All right, greetings, Saintsmen. We are moving on to lesson 4.5. Making sure that I have, need to make sure that I have cameras live for all of you guys who are live in this lesson right now. All right, so we're going to talk about interpolation and extrapolation, as well as the idea of lines of fit. Okay, so what we're going to do is we're going to actually talk about a few things here with regard to analysis. And this is another way that we are going to use some real-life data and try to fit it to our model, or see if our model actually is good for it. You know, this being the year 2020, right? We're in the midst of a pandemic, and these sorts of things, you know, a lot of epidemiology is actually driven strongly by mathematics. So give you actually a little bit of an idea how to understand some of the stuff that you're seeing in the news. The residual here, something that we are going to work with. A residual is going to be the difference between the model and our data point. So let's actually do a real life example here. Let's take snowfall here, okay, versus gloves sold here. So snowfall is going to be in inches, which is going to be X. Oops. And then we're going to have gloves sold, which is going to be Y. What we're going to have here is we have an equation. And our equation is that Y is equal to 1.5x plus 3.5. Okay, and then here's our data. So 1, 2, 3, oops. Two, 3, 4, 5, 6, 7. And our gloves sold, we're gonna have some varying numbers here. We have 5, 8, 7, 10, 11, 12, and 14. So our model is just something we're going to use to try to kind of predict future data. Okay, I'm just going to see if this is actually a good model at all. And what we wind up doing is we have to consider the following, which is the residual, okay? And the residual is calculated as follows, okay? We're going to take the Y value of the model. Okay, so in other words, we're going to take this 1 and we're going to input it here. All right, if we input 1, the outcome that we are going to have is going to be 1.5, 1 times 1.5, right, plus 3.5, and that outcome is 5. Okay, now if we input 2 here, right, it's our next value, input our 2 in for x, 2 times 1.5 is 3, plus 3.5 is going to be 6.5. Now there's a constant increase of 1. This is linear. So we're going to add, it looks like each time here, a common difference of 1.5. If that didn't really make sense to you, just continue to input. We're going to input 3 this time, right? 3 times 1.5 is 4.5. 4.5 times plus 3.5 is going to be 8. Okay? And I'm going to give you guys the rest of these values here, as we could calculate every single one of these, but I'm just going to kind of shortcut this guy for you. Okay, and of course, the last but not least, 14 here. All right, so the way we figure out the residual, okay? The residual is going to be the following. It's going to be the model minus the data point, okay? So in other words, in this case, it's 5 minus 5. The outcome here is 0. Next, we have 6.5 minus 8, which is going to be negative 1.5. Okay. Next, we have 8 minus 7, right? Which is going to be 1. Then we have 9.5 minus 10, which is negative 0.5. 11 minus 11, which is 0. 12.5 minus 12, which is positive 0.5. Then 14 minus 14, which is 0. Okay? So then what we're going to look at here is if we were going to graph this residual, okay, in the coordinate plane. And here we have our residual per value of x, okay? So when x was 1, our residual was 0. When x was 2, our residual was negative 1.5. When x was 3, our residual was 1. When x was 4, it's negative 0.5. When x was 5, it was 0. When x was 6, it was positive 0.5. And when x was 7, again, it was 0. Now, look at your data right here. Look at all these points, all right? These are pretty evenly dispersed, okay? Of the residual are going to be evenly dispersed near the horizontal axis. So therefore, the equation is a good line of fit. That's what it means. What it means is that this thing isn't far off, right? The outcomes. They wound up being pretty spot on and pretty close to what the actual data, what actually projects out. It's this. The more it is on this horizontal axis, it means the more accurate that our model is. It means that the real life data fits onto that line. It's going to be an even fit. Now, it's not a perfect fit, otherwise all the points would be on that line. But give or take a few data points, right? There's some of these guys that aren't on there. And, you know, in this case, this is a negative residual. In this case, it's a positive residual. Means that we're more or less close to it. And it's not necessarily like good that it's negative or bad that it's negative or good that it's positive. That's not what that means. It just means that it's relation to the actual model, right? So we don't want this wild scatter across that horizontal axis. We want to see that it's going to closely fit. All right, so that's going to be kind of our first example of explaining residual. All right, so let's actually use these things. Let's do another model. We're going to take a week, and we're going to take the high temperature in degrees Fahrenheit. Okay. So we have 8 weeks, and then here is our model here, 48, 43, 42, 40, 45, 56, oops. '67. And 76. Okay, so this table shows the high temperatures on Monday for 8 weeks. The equation y equals 7x minus 8 is the model a good fit? So let's take a look here. And I'm going to move this guy up a little bit so that I can actually calculate my residual a little bit better here, okay? All right, so here's my x and here's my y. My y and my x, so y being dependent on x. Okay, so here we go. So let's go and actually calculate out here our model, right? So we're going to model y, okay? So again, we're in input 1 here, right? So 7 times 1 is 7 minus 8 is negative 1. On 2, 2 times 7 is 14 minus 8 is going to be 6. 3 times 7, 21, minus 8 is going to be 13. 4 times 7 is 28, minus 8 is 20. 5, right? So 5 times 7 is 35. 35 minus 8 is 27. 6 times 7, 42. 42 minus 8, 34. 7 times 7 is 49. 49 minus 8 is 41. And then we have 8. It's going to be 8 times 7 is 56. 56 minus 8 is 48. So now let's calculate residual. Remember, residual is going to be the model minus the data. So negative, this one's tough. It's going to be negative 1 minus 48 is negative 49. Ouch. Right? And then we have 6 minus 43, right? We're going to have negative 37. 13 minus 42. Which is going to be negative 29. 20 minus 40 is negative 20. 27 minus 45 is going to be negative 18. 34 minus 56 be negative 22. Then we have 41 minus 67. It's negative 26. And we have 48 minus 76. This is negative 28. So what happens when we actually graph this? So I'm sorry, I think I actually did this wrong here. Should be the model minus the data, not the data, right? or data minus the model. It doesn't really, it's not going to really have any bearing in this case here, because even if I were to do it the other way around, you're going to have these wild swings anyway, right? So even though we have a lot of negative correlation here, it's going to be, I'm going to go by tens here. So 1, 2, 3, 4, 5, 6, 7, negative 10, negative 20, negative 30, negative 40, negative 50. And you guys are going to see here, so 1, it's going to be negative 49, 2 is negative 37, 3 is negative 29, 4 is negative 20, 5 is negative 18, and then we have negative 22 for 6, and then 28, right? So you guys see this U, upside down U shape? Okay, and this means that it's not a good line of fit. It's not linear. All right, moving on here. We're actually going to pause right there, guys, and that's going to be the extent of our work for today. One thing that I want us to take a look at is in the textbook, there's one more thing which they discuss, which is, and we're not going to work with interpolation and extrapolation so much because it's using a linear regression, which we're not going to utilize. If you guys don't know really how to do one of these things by hand, it's actually a little bit complicated. A graphing calculator does this very well and very easily. So we're going to discuss this notion of correlation and causation. Okay, so causation is the following. Causation produces a strong correlation between two variables. Okay? In other words, one variable causes a change in another. Okay? One thing that we do need to make sure that we establish is that correlation and causation are not the same thing, okay? Just because something is correlated doesn't mean that it causes the other thing, okay? So, for example, there might be just a casual relationship with something. So let's compare a few things here. Let's take, for example, time spent babysitting and amount of money earned. Okay? So, we're going to see if there is there a correlation, and also is there a causal relationship, okay? Here, the answer is the following. There is actually positive correlation and a causal relationship. Okay, and the reason why is because the more time spent working, the more money earned. And here, babysitting is a form of working, okay? Here's another one. Eating organic food and getting a good score. Okay? And here, this is one of those things where there may be positive correlation. As possible, okay? But there's no causal relationship. I'm sorry, casual. I keep saying casual. It's causal. Causal. Misread that word a few times there. My apologies. There's no causal relationship. And the reason why is that just purely on the, from the outset, that eating organic food will not cause a good test score. In other words, it's probably a coincidence when these things happen at the same time, okay? Like you just need nutrition in general, which you can get from anything, okay? And not anything, but just non-organic foods. So, again, there are some things that, we discussed this in class briefly. Wonderful book, again, that actually discusses this, and I think very attainable for you if you looking for something to read over the break, is a wonderful book called Freakonomics that does, I think, a good job kind of tackling this issue of correlation and causation. Is one of these things a cause of another? So, so go ahead and get started. I'll have your assignment posted on Canvas. Good luck.